Hi guys, Miss Francis here, and today we're going to talk about using statistics in science, specifically what uncertainty is, what it means, and what standard deviation is. The first thing that we did in class today was we took a quiz on academic integrity. It's really important that your work is not stolen. You guys spend lots of time, hours I'm sure, doing your lab reports, so you don't want anyone to use your work and claim it as their own. So this was a little quiz that we took regarding academic honesty. So we did this lab all about how animal behavior is going to be affected by various variables. So how are you going to present your data? Well, you're going to present it in a data table. So if we notice a couple of things in this data table, you'll see as circled, we've got hours plus or minus 6 hours, or here you've got plus or minus 0.005 grams. Well, where did that come from and why do we need that? And what that is called is uncertainty. Why is there uncertainty? Because there's no such thing as a perfect measurement. So how do we figure out our uncertainties then? If we're using an analog instrument, it's plus or minus half the smallest increment. If we're using a digital instrument, it's plus or minus 1 in the least significant digit. So let's take a look at some practice. This ruler, is it analog or digital? It's analog, so it's going to be plus or minus 1 of the smallest increment. So let's say we measure 2.45. Well, then it's going to be plus or minus 0.01. Let's look at another example. Again, analog, not digital. Let's say this is 24.2. So here our uncertainty is plus or minus 0.1. Let's try another example. Digital. So now our uncertainty is plus or minus 0.5 of the smallest significant increment. So here's our smallest significant increment. So it's going to be 0.0001. Our scale, this is a digital scale. It measures 0.83. So our uncertainty would be 0.01. Same thing here. It's a digital scale, but notice it only goes to the 10th place, so our uncertainty would be 0.1. These uncertainty values are going to be included to show that taking measurements isn't always perfect. And there are two types of errors that come from uncertainty. You've got random errors and systematic errors. Random errors occur once in a blue moon. They're unpredictable. They're unknown. So let's say I measure the mass of a ring 3 times and I get 3 different values. Maybe I forgot to calibrate that machine in between measurements. Let's say that I'm using a meter stick and someone bumps into the table and that meter stick gets jolted. That would be an example of a random error. On the other hand, systematic errors are errors that continuously happen. So it's associated with the instrument or the technique that the human is doing. So for example, the instrument was improperly zeroed, so it consistently reads the wrong mass. Let's say I've got a thermometer and it consistently reads 1 degree higher, 1 degree lower of the actual temperature. If I'm calculating something and I consistently plug in the wrong formula, those are examples of systematic errors. And systematic errors will be discussed in your lab write-up. So why is this important? Well, I must account for uncertainty when performing this experiment. So how am I going to do that? I'm going to present my data in labeled data tables. You see how I have it labeled here? And I have my uncertainty of my measurements correctly identified. But data tables aren't enough. Quantitative data has to be shown in other ways, and the other way is by a graph. This graph might look a little different than the ones that we've seen before. It has these, what are called error bars. And where do those error bars come from? They come from standard deviation. So a couple of things that this is missing that I want you to include in your graph. Obviously, you always need a title. On your graph, you're going to have the dependent variable, which is going to be the number of whatever organism you used. And the independent variable will be on the y-axis. And a lot of kids think that time is going to go on the y-axis. Time was just a tool used to enhance and keep track of your data. The independent variable is actually what you chose to investigate. So pH or light intensity or temperature or, whatever variable you had chosen. So we tried a practice problem in class. It was number 33. I have that handout. But again, how am I going to calculate these error bars? Through what's known as standard deviation. So here's our formula for standard deviation. You do not need to memorize the formula. It is on our reference sheet, and we will actually use a website to calculate standard deviation. So why would we use standard deviation? It's going to tell us how much our data deviates from the average. You, in general, want a low standard deviation, meaning that there is less range within your data. So if we take a look, this is where we want our data to fall. This is our mean or our average, and we want to go one standard deviation above to one standard deviation below. This is our ideal standard deviation values. So let's do an example. Suppose you counted the number of pill bugs that prefer the wet side versus the dry side. You perform 2 trials by recording the number of pill bugs every minute for 6 minutes. First step, you're going to find the mean of each one, and I've already done that. So the mean here is 5.3, but now the mean here is also 5.3. But look at the actual data from trial 1 versus trial 2. Do you notice that there is a wider range in the data in trial 2? And now, what would you expect the standard deviation to be between trial 1 and trial 2? That's right, this should have a much smaller standard deviation, meaning the numbers range less from the average. And if you calculate it, it actually comes out to about 0.5. If you calculate this over here, it's 3 point something. I'm going to just say it's 3.2. So how would we construct a graph that represents our data? So first of all, we're going to put our dependent variable and our independent variable on either side. We want our number of pill bugs, and then we want trial 1, and we want trial 2. Well, in both cases, our average was 5.3. So trial 1's average was 5.3, and trial 2's average was 5.3. I could put bars in if I want. You don't have to put the bars in if you don't want to. You could just leave the dots. But now I need to add my error bars. My error bar for trial 1 is going to be much smaller than my error bar for trial 2, right? Because this one is plus or minus 3.2 something. Nope, these are not drawn to scale. So let's take a look at what error bars mean. If 2 error bars overlap, you can conclude that the difference is not statistically significant. So if we look here, our error bars overlap, and when we look here, our error bars overlap. But what does that mean with respect to our pill bugs? It means that there is no difference between their preference for wet or dry conditions. There's no statistical significance in their difference for either one of those conditions. However, if we look over here, let's say this represents wet and this represents dry, there is no overlapping error bars. That indicates that there was a statistically significant difference between whether the pill bugs preferred the wet environment versus the dry environment. Here is another example of what a graph with error bars looks like. Again, you can note where the error bars overlap and where the error bars don't overlap and what that indicates. All right, moving on, the chi-square test is another statistical tool that we will use to evaluate our data. That will be in our next video.